And if you're looking ahead, guess what? There's no homework due at the end of this. So, and actually, I was talking to, because my husband and I, we sync our classes, and that includes like our exams, so it's kind of fun. But we haven't really given a problem on an exam like this, I don't think. But I remember we had this conversation, and he said, oh yeah, you remember that one problem? I'm like, oh yeah, I remember that one problem. So, but this concept is very similar to the homework that you guys have been working on that was due for today. So you see 3 elementary steps, and overall reaction of interest here is here at the bottom. And then we talked earlier that if you want to come up with the rate law expression, what you need to do is focus on the slow step. And then use molecularity. It's the only place where actually you can use the stoichiometric coefficient of 1 and 1 as the reaction order of B and C. Isn't that cool? So we could go, next slide, you're going to see rate is equal to the molar concentration of B raised to the first power times the molar concentration of C raised to the first power, right? Because it's the slow one. But you know what the problem is? B is an intermediate. You know it's an intermediate because you don't see it down here. Okay, so we're going to have to fix that. And this is to try to kind of convince you how you can get a reaction order that's not a whole number. Okay, a reaction order, there's little superscripts, that's not a whole number. So yeah, in order to come up with the rate law expression, we would focus on the slow step. And like I said, we can use molecularity and to come up with the rate law expression using that second elementary step. So that's why it's K2, because it's the second elementary step. And the molecularity involves an intermediate molar concentration of B. So when this is the case, it's like the homework where we can turn our attention to the fast step before it, which was an equilibrium step. And we can do some algebra and then come up with something B in terms of something that's not, B in terms of something that's real. Okay, so the elementary step in front of that slow one was this one. And so we said if it's at equilibrium, okay, the rate in the forward direction is equal to the rate in the reverse direction. In the forward direction, we use the molecularity of A times K1. Going backwards, we use the molecularity of B, which is 2, okay, times K minus 1. We set those equal to each other, and then we're going to solve for B, okay? So in this case, actually, since B is squared, we're going to ultimately have to take the square root of stuff. Okay, so we can divide both sides by K minus 1. Okay, and then like I said, to get to the B itself, we're going to have to take the square root of that. So are you guys okay with the square root? Taking the square root is the same thing as raising it to the 1/2 power. It's the same thing. Okay, and there's where we get our kind of halvesies sort of going on with regard to reaction orders. So now you know what we're going to do. We're going to go take this quantity and substitute it back into our slow reaction rate expression. Okay, that's what we came up with earlier. Got to get rid of the B. Now we know we can substitute that quantity in for the B. So it's going to be that times C. And kind of like cleaning things up like we did in Friday's lecture. Okay. We usually kind of just talk about one general K. In this term, in this case, looking behind the scenes, K is actually the rate law constant for the second elementary step divided by K1 over K minus 1, all raised to 1/2 power. But okay, so there's where you get a reaction order that's not an integer. The reaction order of A is 1/2. That's it, we're done. That's the rate law expression. So that was the 1/2 reaction order. Let's look at this one. And when we do the math, it's very similar. We're going to come up with a reaction order of 3/2. So this is a little bit different, very similar. We're going to focus on the second elementary step, right? Because it's the slow one. Okay. Can't remember what I've got 2 here. So focusing on the slow one, the rate law expression using molecularity. Remember, we can only know the reaction orders for reactants if it's an elementary step. from its stoichiometry. So like before, B doesn't show up in the overall reaction of interest. B gets crossed out, so B needs to be, is an intermediate. So we need to find that intermediate, molar concentration of that intermediate in terms of something that is real. Okay. So here we go. Luckily, the elementary step above that was this one, this fast to equilibrium. So from that elementary step, we can come up with, the rate in the forward direction is equal to molar concentration of A raised to the first power times K1. In the reverse direction, it's the molar concentration of B raised to the second power, K minus 1. Okay, again, trying to get B by itself, we're going to end up with a square root again, aren't we? It's very similar. Is this not identical or what? It's like deja vu. Okay. So now we know that our intermediate in terms of something real is basically A raised to the 1/2 power times K. Okay, so now what happens when we substitute in is basically, can you see where we're going to have an A to the 1/2 power times an A? Okay, if you have the same base, like we have A is the same base, we can actually add their exponents. So A to the 1/2 times A to the first is A to the 1/2 plus 1, or A to the 3/2. Okay, so we end up with this. Take 1/2 plus 1, and that gives you 3/2. And that's it. So the reaction orders, it seems like forever ago when, we kind of said A plus B goes to form C and D, and we came up with a out-of-the-box generic rate law expression for that. Seems like forever. Those reaction orders of the reactants, we have to get them experimentally. If we know it's an elementary step, we can use the molecularity. Okay. Only if we know it's an elementary step. Okay, so this is, and I've done this other semesters.
Is this